Hey guys, I'm gonna do a short lesson, continuing our our talks about rotational motion. I have a few new ideas I want to kind of introduce today. Before we've been talking about balance and things like that, and how a lower center of gravity can lead to better balance. Balance means not rotating, right? And you sometimes think of like a high wire walker. Some of you guys may have seen this thing on my desk before. This little wobbly guy, and it's kind of supposed to simulate a like a high wire walker. By the way, not exactly. Obviously here there's a lot of weight on the two sides of this, which means this little guy's center of gravity. The center of gravity of this whole system is really low. If this were an actual high wire walker, these wouldn't be bent down. They'd be bent a little bit, but the heavy ends would be kind of here. I may have mentioned before, just a couple weeks ago, there was a high wire guy, Nick Walenda. He's kind of a famous guy for that, kind of like a circus act. He did a high wire walk over an active volcano in Peru, and he had a big, long rod that he was carrying, as those guys do. And that rod doesn't really lower their center of gravity. Same time that you're balancing on a balance beam, you kind of hold your arms out like this. Holding your arms out like this, you do that instinctively to balance. That doesn't lower your center of gravity, right? So what else is going on? Okay, so let's look at my meter stick again here. So I have my yardstick. All right. Now, I have two rocks that I pulled out of my yard. I just moved, and so I have no yard. It's filled with rocks and dirt right now. So I'm trying to make do with what I have around me. So these two rocks are serving as masses. Now, I can certainly make this balance. Okay, each of these are probably a few hundred grams. I would estimate of mass, and that mass has weight. And I'm going to scoot this weight all the way out to here. Now, they're not the exact same weight, so they're not going to be equally distant away here. Now, when they're kind of far away, I can balance this. Okay, so right now they're both creating a torque, but because of how I have everything situated on here, the torques are equal and the whole system remains balanced. And I can move this around side to side. It's pretty stable. Okay, once I find that balance point, it's relatively stable. But if I keep these same two masses here, so remember why this is balanced, is you have equal torques. This one is creating a, I'll turn around with the video here. From my perspective, at least, this one's creating a counterclockwise torque, and this one's creating a clockwise torque. It'd be probably reversed for you folks. And it doesn't rotate because those torques are balanced. But if I move these both in here, so I'm not changing the mass, I'm not changing the torque at all, I'm just resituating them, and I get this closer to the center. Now, do you think that this is going to be more easy to balance when the weight's closer to the center, closer to the axis, or far away? We just saw them far away, and we saw it was pretty stable. So now when I bring these closer in here, what do you think is going to happen to its ability to its stability, its tendency to not rotate? Okay, now here I can definitely still make this balance, but it's hard. Okay, certainly not as stable. It wants to kind of go one way or the other. This isn't a great example because these are on tape, not like a string, but it loses a lot of that ability to balance very well. And again, I should have this attached with string instead of tape because it's kind of self-correcting. But maybe a better example is, I don't know if you have something you can do this with at home. If I hold it like this, it's pretty easy to rotate. However, if I have these weights way out here, it's a lot harder to rotate. I feel a lot more resistance. Something about this weight being spread far apart from the axis makes it more stable, makes it resist rotation that much more. When the weights are closer into the center here, when the weights are closer into the center here, it really wants to rotate. Okay, we can certainly get it to balance, but you know, if I kind of try to disturb it with that, you know, if I kind of give it a little bop, it automatically wants to go. But with the weights way out here, it's more stable. It seems like it has more resistance to rotating. Okay, I give a little bop here, little bop here. Again, it seems way more stable than when the weights were close to the center. Resistance to change, resistance to rotation. It sounds like something we've learned about before. Inertia, you know. From the beginning of the year, we learned about inertia. Inertia is resistance to changes in motion, resistance to acceleration. Small masses don't have a lot of resistance. Large masses have a lot of resistance. Imagine, you know, flicking a ping pong ball. This is the demonstration I do in class. Then you flick a tennis ball, and then you flick a bowling ball. The ping pong ball flies way away. The tennis ball kind of rolls away. The bowling ball doesn't move at all. The bowling ball has a lot more mass, so it has a lot more resistance to change. It has a lot more resistance to acceleration, to changes in rotation. Okay, so what we're trying to get to here is that same kind of value, but for rotation. Okay, so we've talked about inertia before. Now, as I'm looking at this on my computer screen, that's showing up backwards. It's going to be annoying if it doesn't show up the right way for you folks, but well, that says inertia. I'm not used to doing recordings like this a whole lot, so I don't know. I'm just showing up my screen as looking backwards, so whatever. But it says inertia. You get the idea. I don't know if that corrects once I post a video. Probably not. So this is going to be a little bit of a loss. So when we're talking about inertia, when we're talking about linear motion, all that matters is mass, right? More mass means more inertia, means more resistance. But I just gave you an example where the mass stayed exactly the same, and there was a different amount of resistance. There was a different amount of inertia. So something else comes into play here. And that something else is the location of the mass. Okay? Is that mass close to the center or far away from the center? Okay? Now again, this is probably going to show up backwards for you guys, but for what we call rotational inertia, which we indicate with the capital letter I. I is a nice symmetrical letter, so it won't show up backwards for you. Sometimes also referred to as moment of inertia. I don't know, momentum. But rotational inertia, it's like a resistance, resistance to changes in how something's rotating. Now, believe it or not, you actually probably notice this a lot with different things. But whereas normal inertia just has to do with mass, rotational inertia also has to do with, instead of just mass, it does have to do with mass, but it also has to do with the location of the mass. Like how far spread apart the mass is. Is it very densely packed close to the axis, or is it spread really far apart? And rotational inertia has to do with mass and r for radius. Usually that radius is squared. And again, I apologize if this is showing up backwards. But it says mr squared. Okay, so radius is indicative of like the average radius of the whole object. Okay, think of a figure skater. Okay, sometimes they set themselves in a spin and they've got their arms really wide out like this, and then they pull them in, and without pushing off the ice anymore, they then start spinning really fast. So it's a slow rotation with their arms really wide, and they pull their arms and legs tight into their axis, and then that spin speeds up. And it's crazy because that's really one of the only situations in life in which something can speed up without there being a force causing that, without there being a push. That figure skater, and this is also happens when stars collapse, They collapse in on themselves, they shrink, and they have a little bit of rotation out here, and then they pull themselves in. And because of that, that changes how they're rotating. And it's really one of the only situations when something shrinks or expands like that something can speed up without something pushing, without some external force. And that's what's kind of special about it. Okay? And again, you can, let me see if I can set up a demonstration for you here really quick. Alright, I think I'm going to make this work. Got my spinning desk chair here. And I'm going to start spinning myself around. I'm going to hold my arms and legs out and see if you can notice me speed up as I do this. But again, starting a little bored in quarantine here, so starting to do some of my normal physics demonstrations at home. So we're going to start spinning myself around, get a little speed going, arms and legs out. I have a better stool for this at work, and it's a little bit more obvious, but when I reduce that radius, if you can tell, try this one more time. Wide radius, reduced radius. Just sitting there, I can feel a little bit. I don't know how much that translates to video. My eyes are kind of be dancing here a little bit because I'm probably going to be a little bit dizzy. But just like the figure skater, if you've ever seen something like that, or a collapse star, or anything that has some rotation and it shrinks, it will speed up. Okay? Now, that speeding up of how something is rotating is what we call rotational speed. Okay, rotational speed is this symbol. It's kind of a funny looking W. Okay, it's a Greek letter omega. This means how fast something's rotating. If we were doing a lot of math with this, we would measure that in radians per second. We're not. So just think of it like RPMs, rotations per minute. Okay, every object on a rotating, every location on a rotating disk, this point, is all going to have the same number of RPMs. They might all have different linear speeds, but they will all have the same angular speed, or angular speed is another word for rotational speed. So for your purposes, think of it as RPM, rotations per minute or rotations per second. So when I reduced my radius, my rotations per second increased. That's because I changed my rotational inertia, because I changed my radius. I changed my radius, that changes my rotational inertia, and makes it easier for me to have a lot of angular speed, a lot of rotational speed. Okay? So how much resistance something has to rotation is called rotational inertia, also known as moment of inertia, and that depends on two things: how much mass it has and how that mass is distributed. If it's distributed really wide, that's going to make it harder to rotate. Harder to rotate is another word for well balanced. That's why the high wire walkers carry their long stick, because it increases their average radius, it spreads their mass further out, and probably even lowers it a little bit because it does have some sag to it, like my little desk toy here. It doesn't have quite that much sag, but the same principle is that it is increased to this guy's rotational inertia. And if you don't want to rotate, you want a high rotational inertia. If you want to rotate really fast, you want a low rotational inertia. Okay, think about a gymnast, a high diver. As they're doing their end over spins and flips, they tuck themselves into a really tight ball. When they go to land, they want to spread themselves out and slow their rotation as they enter the water or land on the mat or what have you. They do that by changing their rotational inertia. They spread themselves really far out. That increases their rotational inertia, and it slows down their rotation. If they tuck into a tight ball, that speeds up their rotation and allows them to complete more flips or rotations before they get run to the ground. This is why oftentimes a lot of folks that do those kind of things, gymnasts, high divers, are shorter people, because they can they reduce their rate, and it makes them easier to do those rotations midair. So, there's any number of examples where a lot of height gives you an advantage in sports, but there are some where having a more diminutive stature is advantageous. Gymnastics would be the most obvious. High diving and that kind of thing, maybe a little bit too, but mostly gymnastics, I guess, would be the best example of that. And that has to do with their rotational inertia and how that kind of plays into all of that, and how they can manipulate their rate of rotation by doing that. So again, you really only get examples of being able to speed up and slow down without a force causing it in these rotational situations. So when we're also talking about rotating objects, for every rule there is for linear motion, like we learned about the whole first half of the year, there's a similar rule for rotating objects. Okay, an object at rest will stay at rest, an object in motion will stay in motion. That's Newton's first law, and that also holds true for rotation. But just substitute rotational words in there instead of linear motion words. So if an object is not rotating, it will continue not rotating. If an object is rotating at a certain rate, it will stay rotating at a certain rate unless some outside torque, rather than force, some outside torque acts, right? So just like objects can't just apply a net force to themselves to randomly make themselves speed up. Objects cannot just randomly apply a net torque to themselves to make them speed up how they're rotating, right? You always need some outside thing to make you rotate. Now, when you have an outside thing, when you have an outside torque, how exactly you're going to rotate is dictated by your rotational inertia, which is dictated by your mass and how that mass is distributed. It'll rotate a lot if the radius is small. It'll rotate less if the mass is spread way out. But there's some kind of neat things to think about when you talk about rotation, because you can't make yourself rotate. And a fun little challenge I always make, and try this at home. You're probably getting bored like I am. Try to jump up and turn around midair. Okay, now I'm going to demonstrate this for you, and my wife's downstairs working from home, and she's going to hear a bunch of ruckus as I jump up and down. But I think she knows as I bring all these random rocks and tools up into the extra bedroom here to not question what's going on. But it's going to sound a little bit weird, but we'll worry about here. But jump up and turn around midair. Now, at first glance, I'm going to say, that's easy, right? Now, if you actually do this, what you will probably do is you'll stand here like this, jump up, and do that. Easy, right? But that's not what I mean. What I mean is to jump straight up and don't start turning before you leave the ground. Now, if I jump up, if you notice there, as I started to jump up, I was already swinging my arms. Before I left the ground, I was already swinging my arms that way. My feet were kind of pushing off in that way, and so I could easily do that. Don't do that. Jump straight up. Wait till your body is completely removed to the ground before you make anything that turns you to the side, and see what happens. And it'll look something like this. I'm literally trying to turn right now and do exactly what I say, and I can't. I can't apply a torque to myself to make myself rotate. If I do that before I leave the ground is an outside force. It can apply a torque to me sideways, can create that rotation before I leave the ground. Maybe a better demonstration is this. I have this little turntable thing that I got from my wife's grandmother's house before she passed away, so thanks, Nana. I told her I would use this for physics demonstrations, and I continue to do that now. So, little old lady workout thing. So I can stand on this, and it's like one of those things you can imagine an old lady sitting here and just doing this. But that's kind of the point, is if I stand on this, and by standing on this, I'm removing friction from me in the ground, and this I can also demonstrate this in my rotating desk chair. But if I try to quickly rotate to the left, I can't. When I swing my arms that way, my lower body swings that way. For every amount of clockwise rotation I create, there's an equal amount of counterclockwise rotation. Okay? Because the total amount of rotation an object has to remain constant. Like I said, this is kind of Newton's law is adapted for rotating things. Okay? So again, if I twist really much like this, I'm not going to go anywhere. I'm on this frictionless thing. I need an outside torque. So if I rotate one part of my body this way, another part, my hips, my lower body, rotate the other way to keep the total amount of rotation 0. Same way, if I just kind of jumped off from the second story of my house and tried to turn around before I hit the ground, I couldn't. Okay? Now if you're a skydiver, you're like, oh, well, skydivers rotate all the time. That's because they're moving fast enough they can use the air to create an outside torque to make them rotate and flip every which way or whatever. So that's a little bit different situation. But that's kind of one of those things, like, you ever play basketball or something like that where guy shoots and you think, don't leave the ground, because once you leave the ground, you're kind of committed. You don't have anything to stop you to rotate or whatever. So you need an outside torque. And that rule is that the total amount of rotation you have has to remain constant unless there is an outside torque applied. That's true if there's no rotation or if you have some rotation. If you have some rotation, you're not going to be able to stop yourself from rotating. Now, you can change the rate that you're rotating by changing your radius in different ways, but you cannot generate rotation from when there is none. Okay? There's a way that you can kind of change your angular position by just kind of swings here and changing your radius while rotating, but you cannot generate rotation from when there is none. So if you try to do that little turnaround, flip around thing, and you're like, oh, I can totally do it. You can't. You are rotating before you leave the ground. If you find yourself completely turned around, odds are that you have, and if you're really cheating, you could even do a whole 360 or even more. I can do that. I'm, old and out of shape. So you can't, you can kind of change your body position a little bit if your arms are in and you bring them in tight, but you really can't. If you're really getting an easy full rotation or half rotation, that means that you are leaving the ground, and it's really actually kind of hard to leave the ground without rotating at all, because you're just like, yeah, I'm going to jump and turn around, and you're already kind of pushing yourself. You have to wait until you leave the ground midair and then try to rotate, and you will wind up looking silly, just like I did as I was demonstrating that a few moments ago. Okay, so this whole idea is that the total amount of rotation something has must remain constant. What do I mean the total amount of rotation? The total amount of rotation something has is what we call angular momentum. Again, I think this is showing up backwards for you, but angular momentum we indicate with the letter L. L is equal to I times omega. You can see that. Again, that's probably showing up backwards for you, so I times omega. This is rotational inertia, and this is rotational speed. This is what we call angular momentum. Now, depending on the exact shape of the object, this has a different equation. If we're talking about a rotating cylinder versus a rotating hoop versus a rotating sphere, they all have slightly different equations for rotational inertia, but they all have an m and an r squared in there. And so we're going to kind of stick to the conceptual part of this now. So this product, these two things multiplied together, rotational inertia, which is dependent on mass, and radius, and rotational speed, how fast something's rotating, think RPMs, has to stay constant. That product has to stay constant unless there is a outside torque. So that is to say that it must be conserved. So if this goes down, we shrink the radius, this I value gets smaller by a lot. Which, what do you think happens to compensate for that? This rotational speed gets bigger. That's what you just saw me do as I was spinning around my desk chair. Is that when you have a small I, you have a big omega. Conversely, when you have a large I value, you are going to have a small omega. This isn't the most convenient way to write this, I realize, but this product has to stay the same. When R goes down, this goes down, and this goes up. When R goes up, this goes up, and when this goes up, this goes down. Look up spinning figure skater on YouTube. I can't show a video within a video here. I'd show you one. But oftentimes at the end of routines, figure skaters do this really cool maneuvers that are winding down. And they always do it as their last maneuver because I would imagine they're pretty dizzy after it. Is that they set themselves in a slow rotation, then without pushing off the ice anymore, they just pull themselves in really tight, and then this is crazy fast spin. They can do it because they're awesome athletes, way better than I can on a old desk chair here. But that's the principle. And again, stars, when stars collapse, they shrink. They have a little bit of rotation like this, and then they collapse. As they shrink, they speed up. And as I said for the 5th time, one of the only times in nature where you can see something speed up without an outside force causing it. There's no outside force. All it's doing is shrinking. Forces are all internal. And because of the relationship between rotational inertia and rotational speed, with reduced radius, with reduced average radius, comes increased rotational speed. Okay? So again, that product of I and omega, rotational inertia times rotational speed, that's called angular momentum, like rotational momentum. How much, a way of describing that is like how much an object that is rotating wants to stay rotating. And just like I said, it's the rotational counterpart to linear momentum. And we have a law of conservation of linear momentum that we talked about for a long time earlier in the year. And now we have a law of conservation of angular momentum, which is one of the cooler laws of physics because it creates a lot of weird things. Okay, my video is getting kind of long here, so I'm not going to go on for too much longer. But why things speed up as they shrink, why things speed up as they rotate, why they shrink, that's caused by conservation of angular momentum. Why things slow down if they expand, that's conservation of angular momentum. Now, see if I have a few things to help me demonstrate here. Another cool effect of this is, get myself situated. Okay, so I have a quarter here. Okay, can I balance this quarter on its edge? No, I cannot. I can sit here all day, try to balance this on my edge, on its edge. But what about if I roll it across this surface here? It's not exactly a flat surface, but it will stay upright for some time. If I have a nice long flat surface and still get on video, okay, I made it all the way across. It can definitely stay upright then. Or even better, if I spin it. It's a fun game to try. I always like to spin a quarter and try to stop it. Catch it there without tipping it over. Oh, almost had it. But when a quarter is spinning like this, it will stay upright. If I was on a really good smooth surface, I could probably spin this for a good 30 seconds or so. It's like the fact that it's rotating makes it want to stay upright. It didn't want to stay upright at all. It's not rotating. What about rotating things makes it stable? This is true for a bicycle too. You ever try to sit on a bicycle, like a two-wheeled bicycle, without it moving, don't pedal, just totally not moving, and see if you can balance? You can't. Beyond like a second or two, it's always going to tip over one way or the other, and you have to put your foot down to catch yourself. But as soon as you start pedaling, It's almost like it's really easy. There's like zero chance. Just like that, there's zero chance of it falling over. You ever think about that? Like, we all probably learned how to ride a bike when you're younger. The training wheels on at some point. I know I did. What about the fact that it's moving makes it not want to tip over? Has to do with angular momentum. Because angular momentum doesn't just have an amount, doesn't just have a magnitude. The magnitude is determined by how fast it's rotating, its mass, and its average radius. But it also has a direction. Now, if you're thinking about this quarter, you might say, well, the direction it's going is this direction as it rolls across here. And that would not be true, because object can be rotating in place. I'm going to have a bicycle wheel here that I took from work. Hopefully Mr. Packus doesn't want this. Nobody's telling me. But this is rotating in place. This is rotating in place. It's not moving this way or that way. So what direction is its angular momentum? We have a rule for that. And it's going to be confusing because I think this video flips it around like a mirror image. Still not sure about that. I'll have to see what it looks like when I post it on YouTube. But for this, we call that a right hand rule. So this is my right hand. Okay. You might be looking at this video and it might appear that it's my left hand, but this is my right hand. So the right hand rule is this. You take your right hand, you take your fingers. So if this is spinning this way, you curl your fingers in the direction of rotation, and the direction that your thumb points is the direction of the angular momentum. So right now, I follow the right hand rule, point my fingers in the direction of the rotation, curl my fingers in the direction of rotation, and my thumb is pointing that way. My thumb is pointing towards you. That is the direction of angular momentum. Seems weird because nothing's actually going that way. But that is the way that we define angular momentum. And it's also opposite because clockwise is the negative direction. Counterclockwise is the positive direction, which is confusing. That's not super important to you. I do want you to understand that angular momentum has a direction as defined by this right-hand rule. Curl your fingers in the direction of rotation. The direction that your thumb points then tells you the direction of the angular momentum. Why is this important? That's important because every time that you ever see something that is spinning, be more stable. That could be a spiral football, that could be a pitch in baseball, that could be a basketball that you shoot, that could be your bicycle wheels, that could be anything. Again, I have lots of sports examples there. But things that are rotating are inherently more stable. Because this bicycle wheel, if this is going along the road, if this is rotating that way and it topples over, the direction of angular momentum would change. The direction of the angular momentum would go from being in that direction to being in that direction. It doesn't like that. It wants to be conserved. Just like an object in motion, an object that is moving at a certain velocity, it's going to stay moving at that velocity unless some other force acts on it, and it's going to be staying in that same direction as well. Sorry, I heard the cat meowing outside the door. It distracted me. It doesn't just want to sporadically change. It has this natural tendency to stay conserved because angular momentum, the product of mass, radius, mass, radius, and rotational speed, has a direction. That direction wants to stay constant. So by toppling, it would change that, and it doesn't like that. Okay, so this creates all kinds of weird things. This bicycle wheel automatically starts adding stability, and it'll start to roll across the ground, whereas if I try to just balance this on its end here without it spinning, it's always going to, I can't, just like the quarter, I can't get this to tip over. But, I can certainly get it to roll across my desk, trying to not have it crash in my computer here. But so much so that, because this has a lot of mass far away from its outer edge, it creates a almost gravity-defying amount of stability. So if I rotate this like this and really get this going, okay, now first, notice that I do this and I just try to balance this here, it's going to tip over, okay, just as you'd expect. It's going to tip over just like that. But when I rotate this like so, it seems to defy gravity, and it's actually super duper stable here. Kind of like it has a sense to kind of process its way around, but this is weird, right? And when it's spinning, it's actually really hard for me to rotate this. This is the point in the class where I'd usually tip this around. When it's not rotating, I can do this really easy, no problem. But when it's rotating really fast, it's like it's fighting. It doesn't want to let me do it. Same reason it's going in, you know, where it acts as a top. You can get that on video there. And it'll act as a top, and even while its kind of top is processing and swinging around like that, there's a lot of stability. So why are rotating objects more stable? Because of conservation of angular momentum. Why can you not create rotation out of nowhere without something outside of you pushing you? Conservation of angular momentum. So, a few more demonstrations with this tire is I'm on a rotating desk here that can rotate here. My feet are on the ground. I'm going to get this rotating. I'm going to lift my feet above the ground. And when I change this, there's a good one. I'm not pushing. I know you can't see my feet right now, but I didn't push myself. My feet are totally off the ground. My feet are on the ground now. Sorry. Let's go in the other direction. My feet are off the ground. Just by flipping this, it makes me rotate out of nowhere. I didn't do that to myself. If I change the direction, it changes me back. Why does it do that? Because me and the wheel are a closed system. It's rotating, say, clockwise. As soon as I take my feet off the ground, we stay a closed system. And me and the wheel system have all this clockwise rotation. But then as soon as I flip the direction of the rotation, it's made all of that clockwise rotation of the wheel counterclockwise. But what we had initially was clockwise. Sorry if I'm mixing up my words here. And so it makes my whole body rotate in the opposite direction, in the same direction that it was rotating initially, to keep the total amount of rotation, the total amount and the direction of the rotation the same, since we are a closed system. Think about the same time. Every time your body's a closed system, think of it running. When you're running, every time one arm goes this way, another arm goes this way. One leg goes up, the arm goes the opposite direction. You have to have balanced rotation. Okay, that's why your body does it. It's almost like when you're running, it's instinctively. You're not trying to say, right arm goes forward, or left arm goes forward with my right leg, and this arm goes back. Your body's a bunch of rotating parts, and it has to follow all these rules. Whether you're jumping for a 360 dunk in basketball, swinging for a spike in volleyball, or just, simply running. Okay. So there, like I said, all these rules of rotation are kind of governed by these few simple laws. We're going to kind of look at this from more of a conceptual perspective. So, in closing, a couple new things we talked about today: rotational inertia, which is basically how much resistance something has to its changes in rotation. That's a function of mass and radius, as well as angular momentum, which is the product of rotational inertia and radius, and conservation of angular momentum, which means that the total amount of angular momentum always has to remain the same, which means big radius, low rotation. Small radius, fast rotation. All right. In combination with this, I'll give you guys a worksheet or something like that to be determined. But I kind of want to keep this pretty short and largely conceptual. But just kind of some neat things to think about. But remember, rotating objects more stable, because not just the amount of angular momentum needs to stay constant, but also the direction of it. Okay. Also remember the right hand rule. Control your fingers in the direction of rotation. Thumb points you in the direction of the angular momentum. And I think that was it for today. I think there's a couple other demos that I could give, but I'll cut it short. Also, there's a cool conversation about cats and how cats can always land on their feet. See if my cat Lola makes a guest appearance for that. She's being shy right now, but probably find a video for you for you here before we finish up this section. Okay. See you guys later.